Hello everyone and welcome to this lecture on gradient descent, introduction, definition and applications. In this session, we will explore one of the most fundamental concepts that lies at the heart of machine learning and artificial neural network. Before a machine can learn, it must have a way to measure its mistake. For this purpose, we begin with the concept of the loss or cost function, which quantify the error between predicted and actual outputs and serve as the objective and learning algorithm M to minimize. Once we understand how errors is measured, we will see how the gradient descent provides a systematic and efficient way to reduce this error by iteratively understanding model parameters, updating the parameters. Starting from very basic intuition, we will move step by step through single variable, two variable, three variable and general n variable gradient descent supported by mathematical formulations and solved examples. By the end of this lecture, you will have a clear understanding of how models learn from data, why gradient descent is so important, and how it forms the foundation of modern machine learning and deep learning techniques. Let us begin with the concept of the loss or cost function. So here you can see we have the very interesting definition of a loss and cost function. If we go through the definition, a loss function, also known as the cost function, is a mathematical function that quantifies the error between the predicted output of a model and actual output. It provides a numerical measure of how well or how properly a machine learning model performs. In machine learning and artificial neural network, the loss or cost function serve as the objective function. Note this point. Okay, so whenever the term is used in anywhere in the coming sessions, objective function. So the objective function is the loss or the cost function that the learning algorithm aims to minimize during the training. Actually, the cost function is the difference between the actual value or the predicted value, and our main object is to reduce this error. Okay, so here we have the mathematical representation. Y is the actual or the true output and y cap is the predicted output. So then loss function is defined as this is the notation for loss function L y cap. Okay, so the difference between these two values. The cost function is typically defined as the average loss over the entire data set. Note this point. The average loss will be always over the entire data set. And when we will sum up our mathematically notation by using z theta is equal to 1 upon n, summation I equal to 1 to n, L y cap. If there are n, the length of the data set we have is n, and there are two values, one is the actual and the other is predicted. So the average between all these values, we have the cost function. So here n is the total number of the training examples and theta represents the model parameters. So note this point. So here loss or cost function, we can compare these values. Okay, loss function is a single data point and cost function is the entire data set. Okay, and purpose measure individual error, and in the cost measure overall errors, and uses a local error evaluation, and for the cost function it is the optimization objective. So what is the role in the machine learning and artificial neural network? Very clearly defined at this place. The loss or cost function plays a crucial role in the model training, evaluate model performance, guide the learning process, provide feedback for the parameters update, enable automation using the gradient descent. So during the training, the algorithm iteratively minimize the cost function to improve prediction accuracy. Okay, so these are the three common examples. First is the mean squared error. Okay, and simply we can note it by MSE, and we always use in regression problems. Second one we have is the mean absolute error, and its use is in robust to outliers. And last one we have is the cross entropy loss used in the classification problems. So here we will discuss one by one all these three. Okay, so first we have is the definition, mean squared error, how we can define, and then we have the mathematical formula and examples, and also we will try to solve with example. Okay, so mean squared error we have is commonly used loss function in the machine learning and statistical that measures the average of squared difference between the actual value and the predicted value produced by a model. So it quantifies how far the model prediction are from the true output, with larger error being penalized more heavily due to the squaring operations. So if yi is the actual or true value and yi cap be the predicted value, n be the total number of the data points, then the mean square error mathematically is defined as MSE is equal to 1 upon n summation I equal to 1 to n yi minus yi cap square. So this is the square difference between the values. Okay, and then the sum, and we have taken the average. Okay, divided by n. So the properties of MSE, why these are important, what are the benefit? So properties we need to keep in mind while using all these method. These will help us to for the better understanding to apply in the computing part when we do computing. Okay, so MSE is always non-negative. The value which we will calculate will be always non-negative. MSE equals 0 only when predictive perfectly matches with actual values. When the actual values and the predicted values both are equal, in that case we have this is equal to 0. Otherwise we have to reduce the error between the actual and the predicted values. Larger error contribute to more significantly to the loss, and the function is continuous and differentiable. So by using the algos which we are going to discuss here in this lecture, our main purpose is to reduce the error between the actual and the predicted values. Second we have is the role in the machine learning. So mean squared error plays a crucial role in the model training, serve as a cost function for the regression problem, enable gradient based optimization technique, provide smooth gradient for the gradient descent, okay, which we will discuss here in this lecture, and commonly used in linear regression and neural networks. So these are the applications where we will apply. Okay. A loss or the cost function measures the difference between predicted and the actual output and serve as the objective to be minimized during machine learning model training. Okay. Next we have is the mean absolute error, and usually we denote it by MAE. So the definition is very quite simple. Mean absolute error is commonly used loss function in the machine learning and statistics that measures the average of the absolute difference, okay, between the actual true value and the predicted value produced by the model. Unlike mean squared error, MAE penalized error linearly and is therefore less sensitive to the outliers. So here we have the symbols which we are required to use here. Yi be the actual value and yi cap is the predicted value, n is the total number of the data points. Okay, and here in the previous we have the yi minus yi cap square, but here we have the absolute of. So the values which we will take, whether the difference is positive or negative, this will be always positive, and we will divide the sum of these values by n. Okay, so this formula is best is said to be mean absolute error and defined as in this expression. So here are the some properties. MEE is always non-negative. Okay, this will be always positive or 0. MAE equals 0 only when predictive exactly match actual values. When both the values yi and yi cap are equal, only then all the values become 0. If these are identical same, only then we have this will be 0. Otherwise error is the measure to the same unit as the target variable, and MAE is less sensitive to the outliers compared to MSE. Note this point. So there is a little difference between these two when we will apply all this, but some properties are very important, and in the very beginning, if the concept of both we have very clear, then this will help us to choose the technique and apply for the implementation of artificial neural network and how we can optimize the values. So here role in the machine learning and artificial neural network. MAE plays an important role in the regression based learning, mainly when we can use used as a loss function in the regression problem, provide an intuitive measure of average prediction error, produce a constant gradient which may be slow convergence near to the optimum, and useful when robustness to the outliers is required. And only the main key point which we need to keep in mind, the mean absolute measures the average absolute difference between predicted and actual values and is widely used as a loss function in the regression model. Okay, now third one we have is the cross entropy loss, and the definition is cross entropy loss is widely used loss function for classification problem in the machine learning and artificial neural network. Okay, it measures the dissimilarity between the true probability distribution and the predicted probability distribution produced by a model. Lower cross entropy values indicate better model performance. So here we have some conceptual explanation. In a classification task, the model output probability for each class. The true class labels are represented as a probability distribution of one hot encoded. Entropy penalizes prediction that assigns the low probability to the correct class, and confident but incorrect predictions are penalized heavily. Here is the mathematical formula for the same. As you can see here, the true values, the true label y belongs to 0 to 1. Actually, the probability is lies between 0 and 1, or either it is equal to 0 or it may be equal to 1. Okay, so we have to assign the labels either 0 or 1. And predicted probability y cap binary cross entropy is defined as L is equal to, this is the formula, minus y log y cap plus 1 minus y log 1 minus y cap. This is the binary cross entropy loss function. Okay, and categorically cross entropy loss we have is a data set with the n samples and c classes. So L is equal to minus 1 upon n summation I equal to 1 to n summation j equal to 1 to c yij log yij cap. Okay, where yij is equal to 1 if the ith sample belong to the class j, otherwise it will be 0. And yij cap is the predicted probability for class j. And what is the role in the machine learning? Cross entropy loss is the fundamental in the training classification model, work naturally with the probability output and enable efficient gradient based optimization, commonly used with the sigmoid and softmax activation functions. We will use several activation functions are there, and in the coming sessions we will discuss various activation functions along with their properties and which function we need to require for a specific purpose. A standard loss function for logistic regression and neural networks. And here are the some properties. Cross entropy is always non-negative. The loss becomes 0 for perfect predictions and strongly penalized confident incorrect predictions. Provides stable gradient during the training. And here is the main key takeaways which will make more simple and help us to remember in shortly. Cross entropy loss measures the difference between true and predicted probability distribution, and it is the standard loss function for classification task in machine learning and neural network. So now we have very interesting and very useful the part that is the gradient descent. Okay, everything is clearly defined at this place, and we will discuss everything one by one. So first, let's go through what is the gradient descent. It is a fundamental automation algorithm widely used in the machine learning, artificial intelligence, and artificial neural network to minimize a function, typically a loss or the cost function. Actually, main thing is how we can reduce the error between the actual and the predicted values, and this is the main role here to use the gradient descent. Okay, the objective of the gradient descent is to iteratively adjust the model parameters so that the error between predicted and actual outcome is reduced. At its core, gradient descent relies on the concept of a gradient, which represents the rate and direction of the change of a function. The gradient points in the direction of the steepest increase of the function. To find minimum, gradient descent moves parameter in the opposite direction of the gradient, gradually descending towards the lowest point of the function. In mathematical term, if a function describes how error depends on the model parameter, gradient descent provides a systematic and computationally efficient way to determine how those parameters should be updated to improve the performance. This make it especially suitable for a problem involving large data set and high dimensional parameters, space where analytical solutions are impractical. Gradient descent forms a backbone of linear and logistic regression. So here in this example, this is the main figure. So suppose that the initial value we have is this is the gradient. Gradient means the tangent line. This tangent line you can see here, and the initial weight we have is at this point. Okay, so corresponding to here, so we main purpose is to reduce, and this will move towards the lowest point. So you can see this is the lowest point. So main purpose is to minimize this global cost. Okay, so this will always move in this direction, and this point is the minimum. So this is the gradient descent, as you can see in the figure. Okay, so the initial weight is at this point, and this at this point when it will move, this will be the lowest cost. Okay, and this also the learning steps will be taken very small, as you can see. So as much we take the small step, and this the learning rate. The difference between these two we have is the learning rate. So these are the random variable from the initial point, and to reduce the weight. So here is the maximum weight, and at this place we have is the lowest weight. So this will be step by step move to the minimum cost. So from this figure we can easily understand how we can reduce the cost function. So the training of artificial neural network and deep learning and backpropagation algorithm, because of its simplicity, scalability, and effectiveness, gradient descent is considered one of the most important algorithms for the learning from the data. In essence, gradient descent is the machine that enable machine to learn by continuously improving their predictions through error minimization. So main purpose of gradient descent is to minimize the cost function. Okay, so here we are going to start with the one variable gradient descent, then we will talk about the two variable, three variable, and n variable. Okay, so in one variable gradient descent is a automation technique used to find the minimum of a function that depends on a single variable. It is the simplest form of the gradient descent and forms the foundation of understanding automation in machine learning and neural network. Okay, and also this will help you to understand for the two variable and three variable, n variable. Actually, in the real sense, we have the large data set, and many variables are there. So if we start from the one variable gradient descent, this will help us to understand. So let us suppose that the loss function we have is fx. Okay, and then the goal is to find the value of x that minimizes f function. So mainly the gradient is the derivative of fx. Okay, df upon dx, and direction of increase or decrease the rate of change the function. This is the main purpose of the derivative. Okay, here we are taking the gradient descent update rule. This is the rule where by using we can update the same. Okay, okay, as you can see, this is the eta. Eta is this is the main equation. By using this, we can update the values. Okay, so here when we have f(x) is any function, okay, suppose that it is x square. So eta is the rate, learning rate, okay, and we can take the step size which we will choose is the learning rate, at which rate we want to learn the machine. Xk, which you can see here, is the current value, and xk minus eta df xk upon dx, this will give the new value, which is xk plus 1. Okay, so by using this equation we can update the value and see how we can calculate these values. Here we are taking the very simple function fx is equal to x square. This is the convex quadratic function with a global minimum. Okay, so when we will take the derivative, df upon dx will be equal to 2x. So the initial values we are taking, x0 is equal to 6, this is the initial point, and learning rate we are taking here 0.1. So according to the our problem, and this is the not fixed, but we have to check this value must not be as small or much more large. Okay, so according our the problem, we have to choose this value. So in the first iteration x1, from the above equation, we will put all these values, the values of x1 will be equal to x0 minus eta and df x0 upon dx. Okay, so we will put all these values, the value of eta and value of x0 and the value which we compute at its place. So this is equal to 2x0. Okay, x0 is 6. So when we will put all these values, the above equation reduced to in this form, and this will give the value of x1. Now using the value of x1, we can easily calculate the same value x2, which is 4.2 minus 0.1, 2 into 4.4 into 6. Okay, this value is used here, and this after simplifying we have 3.84. Similarly, for the next value we have this value is used here and at this place, okay, in the same function. So the learning rate is 0.1 and the new value is 3.072, and similarly x4 will be equal to 2.4576. Okay, and similarly you can see the iterative summary. These are the x values, and here these are the fx x square values, and when we will compute is for 0, 1, 2, 3, 4, 5. So you can see the initially the value was 36 and now we have 6.039. So as the number of the iterations increase, x will increase, x will equals to 0. So here you can see also the value of x is approaching 0. The value of x is decreasing, and corresponding to that the value of fx is also decreasing. So when x will approach to 0, we have the minimum value of the function. Okay, so here you can see x0 with fx is equal to 0. So this is the global minimum of the function occur at when we have x equal to 0 and fx is equal to 0. But if you will see in graphically, actually the function we have is in this way. Okay, so this is starting from this is the horizontal line from this point. So by step the values of x are increasing. So as x is increasing in this direction, move towards at this place. So at this point we know the value of this function is minimum x equal to x square, as it is a parabolic form, parabola function. Okay, so when x equal to 0, we have fx is 0. So this is the simplest and easiest way to understand how the gradient descent is working here. In the same way, we can take one more example for the two variable, but before that we must go through importance in the machine learning. One variable gradient descent explains the core idea of the automation, and build intuition for multivariable gradient descent forms the basis of parameter learning in the artificial neural network. And key takeaway, one variable gradient descent iteratively moves the variable in the direction opposite to the derivative to each the minimum of the function. Okay, so now here we have the example of a two variable gradient descent. Two variable gradient descent is an optimization technique used to minimum a function that depends on two independent variables. It is a fundamental concept on optimization, machine learning, and artificial neural network. So let the objective function of the two variable is fxy. But before that, I would like to show you one video, and after that we will discuss everything for the two variable. Okay, so see here in this video, this is the three-dimensional. Okay, and that this is the initial point. This is the initial point, and the blue part which you can see in this is the lowest point, and this is the some point which is higher than the upper. So in the two dimension, we have the two variables x and y, and z is a function of xy. Okay, so in the two dimensional we have to take the partial derivative to minimize the height. Okay, so as you saw in the video, the highest point is on the top, and we needed to minimize the difference between the highest point and the lowest point. Okay, so the function will be of a two variable. Here we are taking fxy. Unlike the single variable case, the gradient here is a vector consisting of the partial derivative. So when we will take the partial derivative of f function, we have curl f upon curl x and partial f upon partial y. So curl f upon curl x measures the rate of change along the x direction, and curl f upon curl y measures the rate of change along y direction. The gradient vector always point in the direction of the steepest increase of the function, and here we have these two equations. You can see here xk is equal, xk plus 1 will be equal to xk minus eta curl f upon curl x xk yk, where xk and yk is the current point. Okay, and second we have is yk plus 1 is equal to yk minus eta curl f upon curl y xk yk. Okay, so suppose that if we have this is the three-dimensional something. Okay, and you can see this is the lowest point, and suppose that this is the some point inside xk and yk. This is the xk and yk is any point on the top. So this will, main purpose is to minimize this cost. Okay, so this will take a step size. Okay, when this will be at this point, this is the new value, which is the xk plus 1 and yk plus 1. Okay, so this will move towards in the two directions. Okay, one direction is here is xk, and suppose that along the y-axis this is yk, and this is the point. So this is the new point, and new point is here is xk plus 1, and this is yk plus 1. This is the new value. Okay, so this point will arrive. Then this will take this point, and the coordinate of this point will be xk plus 2 and y k plus 2. So main purpose is to reach this point. Okay, this is the minimum value, and eta is the rate of learning, as we discussed in the previous one. But here the thing is the two variable, so we will take along x-axis and along y-axis altogether. So now here we will solve the real example, and suppose that we have to minimize the function fxy is equal to x square plus y square, and this function represents a convex bowl-shaped surface with a global minimum. Okay, so what we do for that, we have to take partial derivative of this function. Curl f upon curl x will be equal to 2x, and that of with respect to y we will have 2y. So the gradient vector we will have this expression del fxy is equal to 2x and 2y. So suppose that the initial value we have is 4, 6. The x0 and y0, this is the initial point, which is 4, 6, and the learning rate we have is 0.1. So by following the same step as we have defined these two equations, okay, by using these two equations we can update the value. Now the value of x1 and y1, by putting the values in the equations, we have x1 will be equal to 3.2, and that of y1 we have is 4.8. And secondly, similarly we have the second iteration, then we have the third iteration, and these are the iteration steps are here. These are the values of x, and these are the values of y, and these are the values of xy. So from this table you can observe that the value of x and y both are decreasing, and similarly the function fxy is also decreasing. And as you will see that the function we have fxy is equal to x square plus y square. Okay, so actually this function is like in this way. This is a 3-dimension, like in this way. Okay, yeah, like a ball, like in this way. Okay, so this is the lowest point. So if we have any point at this place like xk and yk, so this is the minimum cost. So this will move like in this way, in this direction, as we discussed previously. And at this point, x and y both will approach to 0 0, and f will be in that case 0. Okay, so what we can conclude from this? So the global minimum of the function occurs at x equal to 0 and y equal to 0. Two variables gradient descent, the function of the automation in the machine learning model and neural network training, where parameters are updated iteratively using the partial derivative. Okay. Now the two variables gradient descent minimize the function by iteratively updating each variable in the direction opposite to its partial derivatives. Okay, so here we have the introduction to the 3 variable. As we discussed, for 1 variable, 2 variable, we can extend for the 3 variable. So the 3 variable descent is an automation technique used to minimize a function that depends on 3 independent variable. It is an extension of a single variable and 2 variable gradient descent, and is essential for understanding automation in high dimensional machine learning model. And let's suppose that the loss function we have is fxyz. The gradient of a 3 variable we can have defined as this expression del fxyz is equal to curl f upon curl x, curl f upon curl y, curl f upon curl z. Each partial derivative represents the rate of the change of the function along its respective direction. The gradient vector points in the direction of the steepest increase of the weight, and this is the update rule for the 3 variable. Okay, xk plus 1, xk minus eta, curl f upon curl x, xk, yk, zk. Similarly, we have yk plus 1 and xk plus 1, where this is the current point and eta is the learning rate. And here also we try to put here the problem statement example. This example is the same as we do in the for the 1 variable and 2 variable. So you must go through this example. First we will take the partial derivative with respect to x, y and z, and this is the gradient vector. Then we will choose the initial point, and eta is 0.1, and as we do in the previous 2 examples, here we will update the values by using the iterative updates. So this is the x1, y1 and z1. The values are updated similarly in the iteration 2, and the result x, y, z will approach to 0. Okay, x equal to 0, y equal to 0, and when z equal to 0, this is the point where the function have the minimum value. And when you will put all these values x0, y0, z0 in the above function, that is also 0. So these are the simplest example to put here to understand exactly how these values are changing and how the gradient descent is working. So the importance in the machine learning for the 3 variable gradient descent, build intuition for multivariable automation, forms the basis of weight update in the neural network, extend naturally to higher dimensional parameters. So from these 3 examples we can easily understand how this will extend for the multi dimensions. Okay, so if we have any n dimensional variable, so here is the definition we try to put here. In the machine learning and artificial neural network, automation problem often involve minimizing a function that depends on a large number of the variable. The most general form of the gradient descent considered on the objective function with n variable, and let the objective function is x1, x2, xn. These are the n variables are here. The goal of the gradient descent is to find the value of these variable that minimizes the function. Okay, so actually the thing is we need to find out the values of the parameters which are involving in this function, and on the basis of those parameters the value of the function must be minimum. Okay, so the gradient of n variable, you can see del f will be equal to curl f upon curl x1, curl f upon curl x2, and so on, curl f upon curl xn. Each component represents the rate of change of the function with respect to one variable. The gradient vector points in the direction of the steepest increase of the function. General gradient descent update rule is here. You can see x I k plus 1 is equal to x I k minus eta curl f upon curl xi. Okay, and we will take the derivatives x I 1k, 2k, 3k, and so on, and where I is equal to 1, 2, 3 up to n. Okay, so what is xik? Is the value of the ith variable at iteration k, and eta is the learning rate, and curl f upon curl xi is the partial derivative with respect to xi. So this is the main formula for generation of the above one-dimensional, two-dimensional, and three-dimensional, and we can generalize for all the variables when we have a function involving n variables. And this is the vector form of the representation. If we have x is equal to x1, x2, and xn, the general gradient descent update rule can be written compactly as xk plus 1 is equal to xk plus eta delta f x raised to power k. Okay, this vectorized form is widely used in the machine learning algorithm and neural network training. So from the above discussion we come to this expression, and when you will implement this, then actually the thing is that all the parameters are always in the form of the vector. Okay, so vector representation is very important here to discuss, and by using this one we can find out the optimum cost. So here is the convergence objective as the number of iterative increase xk approaches to x star. X star is the point at which del fx star is equal to 0. This point corresponding to the local or the global minimum of the function. Okay, and the importance of artificial neural network and the machine learning. The general and variable gradient descent formulation forms the mathematical foundation of backpropagation, enable automation in the high dimensional parameter space, and supports scalable learning for deep neural network is applicable to regression, classification, and deep learning models. Okay, so this is very highly useful when we will develop some model based on artificial neural network or the machine learnings for large data set. Okay, so these are the some key takeaways. Gradient in n variable, general n variable gradient descent to minimize a function by iteratively updating all variables in the direction opposite to the gradient vector. Okay, so this is all about the today's session.